measures of variability. And this may be something new to you. Here's where we discuss the standard deviation, which is a very, very important concept in statistics. Before we get started with that, we're going to start with something a little bit more easy. Just the concept of what variability is. If we look at a distribution of two distributions. The first distribution, distribution 1, contains data values that all have the same value. 5 data values with the number 4. Distribution 2 has the numbers 1, 22, 24, 31, 100. Okay, so in distribution 1, we would say that there is no variability. All of the data values have the same exact value. Distribution 2 has variability because the data values vary from 1 to 100. Okay, so we have variability in distribution 2. There is no variability in distribution 1. How much variability in distribution 2 is something that we're going to discuss now. We use measures of variability in addition to measures of central tendency to describe the characteristics of a distribution. The 3 measures of variability are the range, the variance, and the standard deviation. Okay, the range. The range of a distribution is the number representing the difference between the largest and smallest data values. So this is the easiest of the 3 measures of variability, the range. Its calculation is very basic. It's basically take your largest data value, subtract your smallest data value, and there's your range. So in the previous example with the largest data value of 100, in distribution 2 and a smallest data value of 1, the range would then be 99. Okay, so let's take a look at calculating the range here. We have student A with test grades 50, 70, 70, 70, 70, 70, 70, and 90, and student B with 50, 55, 62, 70, 78, 85, and 90. We're going to compute the range for each student. In both cases, the highest data value is 90 and the lowest data value is 50. So the range is 40. You're going to take 90 minus 50 and you get 40. And that's the same for student A and student B. Examine the variability of the test grades for both students. Do you believe that the test grades for both of these students have the same variability? And explain. Well, if we look at the numbers for student A, well, the first number and the last number seem to vary, but the numbers in the middle are pretty consistent. Actually, they're perfectly consistent. It's the same 70 all the way. Student B, take a look at those numbers. They vary considerably from one to the next. Every single one of them is different. So would you say student A or student B has greater variability? Well, you should say that student B has greater variability. Now, how would you know that if you were only provided with the range? The range does give us some degree of variability. It tells us the range of data values. However, it doesn't tell us the difference between two distributions that have the same exact range could have very different data values in between the largest and the smallest. So our answer here is no. While the range for both students is the same, the grades for student B vary more than the grades for student A. The variability of student B becomes noticeable when examining all the test grades for each student rather than just their extreme grades. Okay, so that's how you can answer this question given an explanation. Okay, so a shortcoming of the range. The range gives a quick method for describing variability, but it does not take into consideration the value of all the data values when measuring the variability of a distribution. So we couldn't see that student B had the greater variation of grades just by looking at the range. So we need something more. So moving on, the variance of a sample and the variance of a population. This is going to give us a little bit more information about variability. The variance of a sample of n data values is equal to the sum of the squared deviations from the mean divided by n minus 1. Okay, and here's what we mean by that. The sample variance is equal to the sum of all the data values minus the sample mean squared divided by the number of data values minus 1. Now we're going to take this formula step by step and we will calculate a sample variance. This is how we denote the sample variance using symbols. Little s squared is the notation for a sample variance. We have our Greek sigma for take the sum of, and here we've seen this before, data value x minus the sample mean squared divided by the size of the sample minus 1. For a population, you change the little n to a big N, you change the x bar to a mu, and you'll change the s squared to another symbol called lowercase Greek sigma. And then the denominator here is somewhat different for a population. Okay. Notice that the denominator here, for a sample we subtract 1, for a population we don't. Okay, so this is just the way it's done. The population is just capital N and we don't subtract 1 as we do for the sample. However, all the other things are generally the same. Take the sum of all the data values minus mu, which is the mean of the population, squared, divide by the size of the population, and that equals, this is sigma squared. This is a lowercase Greek sigma, and it's squared. Okay, so we are going to go through this formula step by step to compute the sample variance for the numbers 3, 5, 7, and 9. So the first thing you want to do is arrange 3, 5, 7, and 9 in a column and find the sample mean. So these numbers represent data values x. If we want to find the mean, we'll take 3 plus 5 plus 7 plus 9 and divide by 4. So if we add them all up, that's the sum of all the values x, that's 24. Divide by the total number we have is 4, that's 6. So x bar is 6. That's our first step. Okay, we're going to subtract the mean, which is x bar, from each term in the given distribution. So these are our terms in the distribution, these are our data values, and we're going to subtract x bar from each of them. So in the next column, next to this one, we're going to put x minus x bar, and we're going to put its value. So, for example, the first row, we have a data value of 3, a mean of 6. 3 minus 6 is negative 3. 5 is the data value, 6 is the sample mean, 5 minus 6 is negative 1. And we did this before. At this point, you should note the same thing that we saw earlier, that if we were to add up this column, we do get a value of 0. And like I said before, that is going to happen in every single case. But that's not what we're doing here. We're going to then, next column, square each of the results from the previous step and add up all the squares. So when you square negative 3, you get a positive 9. You'll put that answer here. Square a negative 1, you get a positive 1. Put that answer here. Square 1 is a positive 1. Put it here. Square 9, I square 3, that's a positive 9. Put your answer here. And so your next column looks like that. 9, 1, 1, and 9. Okay, now this is a web work assignment. Your web work homework associated with this lecture asks you to do just this. However, when it comes time to put your answers on web work, don't put 3 minus 6 equals negative 3. Just put a negative 3. Just put a negative 1. And the same thing over here. Don't put negative 3 squared equals 9. Just put a 9. Okay? Just put 9, 1, 1, and 9. Now, your numbers, of course, for your homework are going to be different than these, but don't put an equal sign in your answer. Just put the number. Okay, add up the last column. So we're going to take the sum, capital Greek sigma, of all the x minus x bar squared. So we take 9 plus 1, that's 10 plus 1, that's 11 plus 9, that's 20. Now that becomes the numerator of our variance calculation. So we are going to take that answer and divide by n minus 1. So our sample variance is s squared. That's the notation that we use. We take the sum of all the x minus x bar squared. We got that to be 20. Divide by n minus 1. Well, since n is 4, there are 4 data values. 4 minus 1 is 3, and 20 divided by 3 is approximately 6.6667. Now, variance values are generally going to be taken out to 4 decimal places like we have here. Okay, this decimal place repeats. It's 666 repeating. So if you have to take this out to 4 places, you would turn that into 0.6667. Okay, a population variance is so similar to the sample variance except for that very last step where you divide by n minus 1. When you have the population variance, you divide by n, capital N, the size of the population, not n minus 1. So 3, 5, 8, 13, 21. We first create a column and we list our data values, 3, 5, 8, 13, 21. It doesn't matter if these are sorted or not in ascending order. It does not matter. Okay, the next column, you're going to find the population mean mu, which happens to be 10. So if you take 3 plus 5 plus 8 plus 13 plus 21 and divide by 5, you'll get a mean of 10. So your second column will have 3 minus 10, which is negative 7. 5 minus 10 is negative 5. 8 minus 10 is negative 2. 13 minus 10 is 3. 21 minus 10 is 11. The next step, you're going to take those values in the second column and square them. So when you square negative 7, you'll get a positive 49. When you square negative 5, you'll get a positive 25, etc. So your answers are 49, 25, 4, 9, and 121. And on web work, please, you're going to just put the single answer, not the entire calculation. Your population variance involves summing up this last column, which is this top numerator calculation here. That becomes 49 plus 25 plus 4 plus 9 plus 121. That's 208. Divided by n, which is 5, the size of the population, 5. And that comes out to be 41.6. And the notation for the population variance is sigma squared. Lowercase Greek sigma squared. Okay, the variance is in square